Hello everyone, welcome to this GlobalSpec solar energy event. I'm Jim Brennan. Solar energy has moved beyond the emerging technology phase to become a utility-scale solution for clean, renewable energy. Specifically, concentrating solar power has helped to lead the clean energy revolution by proving its capability for utility-scale solar production. Engineering, procurement, and construction, or EPC, contractors face unique challenges when designing and building CSP plants. They must focus on innovative engineering processes, cutting-edge construction workflows, and industry-leading project management techniques to complete these mega projects on time and on budget. And that is the topic of our next presenter. First, though, let me quickly invite you to submit your questions at any point during this upcoming presentation by using the Enter Question and Submit button at the base of this video console. You can also download a copy of the PowerPoint for note-taking and easy reference just by clicking on the button labeled Download PPT. Our next speaker currently serves as the Vice President of Engineering for Lauren Engineers and Constructors, a design-build leader in concentrating solar power facilities in the United States. He has more than 28 years of project management and civil structural design experience in the power generation, defense, petroleum refining, and industrial process industries. Please join me in welcoming Clint Rosenbaum to our GlobalSpec Solar Energy Online trade show and event. Clint, welcome.
Thanks, Jim. I appreciate the opportunity to come visit with you today. I'm going to talk to you a little bit about why solar. Then I'm going to talk to you a little bit about the different CSP, or concentrating solar power technologies. Then we'll visit some about the role of the EPC contractor in the construction of those facilities. But let's talk about why solar. Solar is a clean, renewable energy. There's no emissions from the solar plants, and there's no variable cost in that we're not having the fossil fuels, the coal or the natural gas, and the fluctuation in prices there that we have to deal with in those kind of environments. So we've got a renewable resource that's directly from the sun with no cost for the power. We have multiple applications. We can put in a greenfield environment where we're doing a plant from the ground up, or we can go in a brownfield situation where we're in existing coal or gas-fired power plants. We can augment the power with the solar heat that we give. We can bring the steam into those plants, or we can decommission the existing coal or natural gas-fired boilers and directly power the steam turbine with the heat that we're getting from the solar field. We also have new and emerging technologies out there where we're improving the technologies, getting better at what we're doing. We have tax credits and renewable portfolio standards with the states where we can drive down the cost. We can do more of these. We can get repetitive. We can bring in the new technologies, and we can all work. And the more we do of these, the better off we'll be, and the more we'll drive down the cost. I want to talk a little bit about the two main technologies here. We're talking about concentrating solar power today, and that's kind of where the presentation will focus on. And it's a solar thermal heat-to-steam transfer of power. But I want to talk just a second about photovoltaic so we can kind of make a distinction or draw a distinction there. Photovoltaic is what we'd call a direct-to-grid power system where we got the black panels, which everybody's familiar with the black panels. We have a black panel that's absorbing the sun's energy, converting that directly to a kilowatt output, and we're gathering that kilowatt output and we're putting it out through the grid on an inverter through transformers. So photovoltaic is the black panel direct-to-the-grid type system, where concentrating solar power is a heat gathering. We gather the heat, we make a steam, and then we turn a steam turbine. CSP overview here. Let's kind of give you the three different technologies that are there. The first one we want to talk about is power tower. It's a receiver, central receiver on top of a tower surrounded by a heliostat field or mirrors. We take those mirrors, they direct the sunlight to the receiver on top of the tower. We have two working mediums, either a water, where we're taking water up the tower and converting that to a steam, or we'll take a molten salt. We'll take a molten salt up the tower, we'll gather the heat inside the receiver, and we'll bring it back down the tower, and we'll use a heat exchanger down at the ground level to take and convert the water to steam. So we'll have a mirror field surrounding a central tower to do that. And here's a illustration of that. You can see the central tower in the center with the heliostat or the mirror field around the tower. Another technology is linear Fresnel. A linear Fresnel has a central receiver that is mounted about 5 meters above the ground. We have the mirrors on the ground, taking the sun's energies and the sun rays and reflect them up to the central receiver. This is a direct water to steam type setup where we bring in water in one end of the receiver and making steam and turning steam out the other side. And the way we make enough steam here is we put multiple lines of these receivers together. You can see that linear Fresnel setup in this picture. The central receiver is mounted about 5 meters above the ground. You got the mirrors at the ground that are tracking the sun and reflecting the sun's energy up on the receiver. The most traditional type, or the most mature technology, is a parabolic trough. We have troughs in a parabolic shape with mirrors that have a focal point of a receiver that's the focal point of the parabolic trough. It tracks the sun from east to west during the day. We have a heat transfer fluid going through that trough and that receiver. We gather the heat from the heat transfer fluid, take it into a central receiving area where we use a heat exchangers to convert the water to steam. Right now, commercial operation, there are 3 plants in the U.S. We've got the SEGS plants that were built in the late 80s. We've got Nevada Solar 1 and Martin Solar, which are 2 recent plants. Lauren has built both of those plants. The Nevada Solar 1 plant came online in 2007, and the Martin Solar plant came on in December of 2010. The traditional type of operation is the solar field. We've got the solar field with the parabolic trough in it. We have the heat transfer fluid circulating through the solar field. We have heat exchangers that we have converting the heat into the water. So we have HTF on one side, heat transfer fluid on one side. We have water on the other side, converting that to steam. We'll take that steam, we'll put it into a steam turbine to make the electricity. Now, Nevada Solar 1 is that kind of a greenfield from the ground up plant where we take the HTF out of the solar field, take it into the heat exchange area, convert the heat into steam, turn the steam turbine. Another type of facility is a hybrid plant, which is the Martin Solar plant. We use the same type of solar field. We have the solar field with the HTF circulating through the solar field. We have the heat exchange. We're converting water to steam, but we're not taking the steam to the steam turbine. We put it into a heat recovery steam generator on the back end of a gas turbine. What that allows us to do is have a mass flow of steam through the heat recovery steam generator during the day, where we can make heat in the solar field. We can cut back on the duct burning in the heat recovery steam generator. Therefore, we can cut back on the natural gas that we're using. We can augment the power. Then we can take that power out of the heat recovery steam generator into the steam turbine. This is a picture of the Florida Power and Light job near Indiantown in southern Florida. You can see the parabolic troughs. You can see the header collecting the HTF, and you can see it going up to the heat recovery steam generators in the background. Where are we doing these kind of plants and what's going on here in the U.S.? You can see that the concentration of projects is out in the western U.S., California, Nevada, and Arizona. There are a few scattered elsewhere, but the main concentration of them is out in that area. Currently, we have 500 megawatts in generation. We've got 1,100 megawatts under construction, and we've got 7,500 megawatts on the drawing boards to be developed. Worldwide, you can see that U.S. is the leader there with a number of projects. Spain is closely behind us. Spain has had a program to develop CSP for a long time, and they're developing that. India has a new program, a solar mission, to develop CSP, and they're beginning to get into the market, and there's a market there in Australia. So worldwide, we've got about 1,300 megawatts in generation. We've got about 2,500 megawatts under construction and about 8,500 megawatts in development worldwide. Now let's talk a little bit about the EPC role and what we do there. The number one thing on the EPC side is a successful project. That's what we're all striving for. And in doing that, we're going to deal with multiple stakeholders. We have owners, developers, we've got power generation companies, local governments, solar field component suppliers, power block equipment suppliers, as well as our own internal workforces and corporate structure we have to deal with. And we're dealing with all of those groups in a contractual type of environment where the owner and the developer is going to want us to put up performance guarantees, or want the EPC contractor to put up performance guarantees. If he's going to want a project that's going to do what we say it's going to do, in other words, if we needed to generate 300 megawatts, we want to know that it's going to generate 300 megawatts with so many megawatt hours per year. Wants it obviously on time, so time of performance is key. He wants to know when he's going to get his project so that he knows when he can start delivery of his product, and he can start getting his return on his investment. And then obviously he wants a low capital cost, because the lower the capital cost, the earlier he can get his project, the more he can start making revenue and the greater rate of return he can get. So in an EPC environment, we want a successful project, but we're dealing with multiple stakeholders in a contractual type of arrangement. So what's the role of the engineer, and when do we want to get an engineer involved? Well, we need to do that up front in the feasibility and the front end studies. And we need the engineer to work right alongside with the owner and the developer to work on his project, to see where we need that project to go and what we ultimately want to do, which is come up with a power purchase agreement where we can deliver that power to the ultimate end user, out to the customer. So we're involved in site selection. Why is site selection important? These projects are large. They're anywhere from 500 acres to 2,000 acres. We need the site to be relatively flat. We need it in an area where we got good solar radiation, and so these are generally in arid environments. We need to watch the environmental. So site selection is important. The engineer needs to be involved in that or wants to be involved in that. We're also looking for a site that has a good water availability resource. If we don't have water available, and in the desert, water is a very precious commodity, so if we don't have water available, we're looking for other methods, whether it be air-cooled condensing or something else, to be able to dissipate the heat that we get. We obviously want to be close to a transmission grid, so we don't have to build miles and miles of transmission. And then we want to be friendly to the environment. So we want to look through the environment, see what kind of environmental impacts we have, mitigate those as much as possible. Now, what are some of the major challenges behind the engineering? Obviously, this plant only works when the sun's there, so it starts up every morning and it shuts down every evening. It's not like a conventional power plant that's designed to run on a 24/7 basis. It'll start up in the morning, it'll run during the day, it'll peak out, the load will levelize during the day, and then as the sun starts going down in the evening, it'll go to sleep. During the day, we also have transients that come through, a cloud cover or some other thing like that, and so there'll be times of the day when the plant will have to slow down or get off of its peak load. So start up and shut down during the day and in and out is very important and something that needs to be handled, and is a big challenge on the engineering side. Obviously, designing for extreme weather. We're usually in a desert environment where we've got heat and dust to deal with. The dust is not good on the mirrors, because when the mirrors get dusty, they lose reflectivity, and we can't gain as much energy from the sunlight as we'd like to. So we have a continual washing process to keep the dust off of those mirrors and keep them clean. In the hurricane area down in Florida, we had to deal with hurricanes, so everything is much stronger. The mirrors are attached much better. There's lots of things that are done to take care of the hurricane environment. And also we have the cloud cover and the transients that come through more readily in the Florida area, so we dealt with that. In India, we're dealing with the monsoons. The Indian air environment has a monsoon season, and so how do we deal with the ups and downs of and in and outs of power generation with the solar in a monsoon season? So we're dealing with that. Another thing is the heat transfer fluid, and the heat transfer fluid running through a parabolic trough system is a Dowtherm product, and it has about a 750, 800 degree Fahrenheit temperature on it. And so we're circulating that heat transfer fluid through the solar field. How we circulate that, how we gather it, how we get it back, how we make the heat transfer into the water and the steam is important. And there's a little art there to doing that. And so we look at that and we watch and we see what's the most economical, most efficient way to doing that. When we're doing these projects, we're working in protected habitats, whether it be in the desert or whether it be in the marshlands. So we're paying attention to what we're doing there and protecting the environment and doing things for that. We also have temperature considerations. Like I said, it starts up in the morning, shuts down in the evening, so everything is cold in the morning, it's starting up, it's expanding. In the evening, it's cooling down, it's contracting. So we have to build in expansion loops, watch what we're doing there, take a heat transfer and expansion into account. Now the heat transfer fluid also will do the same thing. It'll expand as it heats up during the day, and then as it cools down in the evening, it'll contract. So we have to have expansion. We have to watch for expansion and contraction of our heat transfer fluid. And then because of the cyclic nature of everything, the startup and shutdown and the repetitive cycles, everything is thicker and heavier and more robust to be able to take care of the cyclic nature of the facility. And then again, we're working with various suppliers from all over the world. We've got new and emerging technology that we're dealing with. We've got better, quicker, more efficient ways of doing things coming on board every day. The way we're doing projects today may be totally different in 5 years from now with the technologies and everything that we're developing. So another major role the engineers playing is dealing with all of those different suppliers, different new and emerging technologies, and staying on the leading edge of what what we're accomplishing here with our solar work.